presented by Federico Poli, also from ETH Zurich, and it extends the general theme of modular verification with modular specification.
Okay, thank you for the introduction. So, as you may guess from the title, our work is about verification of Rust programs. But actually, the first slide is not about Rust, it's about C. So, I will use this example multiple times during the presentation. It's a simple function. It's a client function that takes 2 parameters. They are 2 pointers, and they point to 2 linked lists. And in this function, we store the length of the second list in a local variable. Then we append an element to the first list. And finally, we assert that the length of the second list didn't change. So now you may be interested in proving some functional property about this program. For example, you want to prove statically that this assertion always holds. But this is challenging. Even for such a simple program, there are some problems with it. For example, the B pointer can be null or may point to uninitialized memory. Or also, you can have aliasing between the 2 parameters. Maybe the 2 pointers point to the same data structure in memory. So when you append something to A, you have a side effect on B. And this is not evident from the code. And finally, if you have another thread that is working on the 2 linked lists that are passed to this client function, you may have data races and this property that you assert might not hold. So now, how do you prove this kind of program using modern program logics? Usually, you have some ingredients. For example, if you want to represent the memory, you may want to model the 2 data structures that are passed to the function. And you can use a predicate to do so. A predicate represents a possibly unbounded set of memory locations. And then you may want to specify that the memory of these 2 data structures are disjoint. So in separation logic, for example, you can use a so-called separating conjunction to specify this property. And then you want to specify, for example, that the list B contains a particular field, contains a field length. And you may want to say that the list B owns this field called length. What does it mean? It means that a function that is allowed to modify the list B is also allowed to modify a particular field of it, for example, the length field. And in this program logics, this how to change from a representation in which you see a list B, how you move to a representation in which you see a particular field of it, is achieved using some auxiliary annotations. For example, whenever you want to replace a predicate with a definition of the predicate, you can use an auxiliary annotation, and the other way around. So these ingredients are very powerful. For example, with such a representation, you can see that if you modify the list A, then what is in the second list B, which is disjoint from list A, stays the same. So it means that the length of the second list is not modified when you modify the list A. This is very powerful, but also hard to use. In a real-world proof, you may end up with something like this, and the ingredients are used all over the places. So you need to be an expert in order to build such a proof. And this is a proof that is mandatory. You have to mix these ingredients before going to verify more interesting properties. So in this talk, I will call core proof this proof that you have to build before going to verify properties like sortedness or whatever else you need. So now let's switch to a different programming language. In Rust, you have, well, this is the translation of the same example in Rust. And we have the same goal. We have some functional properties that we want to verify. And what about the problems that we had before? The difference with the previous example is that now the type of the parameter is, of the parameters is different. Instead of just a pointer in Rust, there is a particular type called mutable reference, and this client function takes two mutable references to two data structures. And it turns out that in Rust, this type system is very useful for the developer because whenever you have a reference, the compiler, the type system, checks that the reference is not null and points to an initialized memory. So you cannot have memory errors like in C. What about aliasing? A mutable reference in Rust owns the memory locations that are reachable from the mutable reference. So since a memory location cannot have two owners, in Rust, these two mutable references that are passed as parameter, A and B, are unique pointers. They point to disjoint memory locations. So we cannot have aliasing, and these two lists in memory cannot share any node. What about data races? The compiler also checks for them, and this is a problem that is solved by the compiler. So we saw that this type system is very useful for the developer because there are some guarantees. The developer can stop worrying about null pointers. And our question is, can we also reuse the same guarantees that the type system gives to the developer to simplify the task of verifying this program? So we saw before that building a core proof is difficult. And in our proof, in our work, we actually reuse the type system information to simplify verification and to build the core proof that we saw before. So this is maybe, it's too abstract. I have a demo. So this takes a few seconds. I have to exit the presentation. Just a second. And the screen takes a few seconds to resize. So this is the same program that we saw before. Let me introduce a bug. For example, if we try to append to B, what happens? I save the program and I run the tool. Our tool is called Prousty, and you see below that it's running. So now Prousty is building the core proof and checking that this assertion, whether this assertion holds, and this does not hold because we introduced a bug. The asserted expression might not hold, so there is an error message regarding this line. If we switch back and we use the correct version of the program, then after a few seconds, Prousty does the translation and proves that this assertion always holds at runtime. So for this example, the example is exactly what we saw before. It's Rust code. And just one line of annotation is needed in order to verify this program. So the developer only has to, for this example, to add one line, this pure annotation that means that this particular method called length actually can be translated as a pure mathematical function. We also have a definition of append, and this is a standard definition in Rust. If the next pointer contains has some element, so if there is a tail for the linked list, then we append to the tail. Otherwise, we create another element and we set it as the next element in the linked list. So there are some more interesting properties that we can verify. For example, we can require that the function can require the first list A to be sorted, meaning that the values in the linked list are ordered. And imagine like integer values. And we can also require that the last element in the linked list is less than 100. So with these two properties, we can ensure that as soon as someone appends an element with value 100 to the end, then the function can also ensure that A is still sorted for the client, for the caller that calls this client. And we can also ensure that the length of the linked list increased by 1. So if, for example, we introduce another bug, for example, this time we change the specification doesn't reflect what happens in the program, then we get a verification error pointing this time to the post condition of the function, this ensures keyword, and Prousty points out that the post condition of this function might not hold. If we fix it and run our tool, then we will see that the function verifies correctly. So you can see it below, verification succeeded. For this example, we wanted to prove some more interesting property, sortedness, for example. We had to pay a cost. We had to provide a stronger contract. We have to specify what the function requires, and we can then ensure something. And for example, let's look at the definition of the sorted method. Again, this is marked as pure, meaning that this can be automatically translated as a pure mathematical function, side effect-free deterministic function. So a definition of sorted is simply, if there is a tail, then we check that the element in the first element of the tail is greater than the element of the current pointer. And then we recursively check that the rest of the linked list is sorted. So back to the presentation. Okay, so what is the approach that we use in our tool? We take some information from the Rust compiler, for example, from the information of the type system, we automatically encode the predicates at the proof level. From the signature of the functions, we encode what is the pre and post condition that we have to specify in the proof for each function. From the information coming from the borrow checker, that is a particular component of the compiler, we automatically encode what are the auxiliary proof annotations that are needed in order to make the proof go through. And finally, from the contract that the developer can optionally add to the code, we can encode the functional specification that is used and checked by the tool. So notice how in this approach, the user only sees only has to know the Rust level of this, what happens at the Rust level. The types, the signature, the borrow checker are something that are already known by the developer, and the contract can be expressed using Rust expressions. So our tool, as we saw, is called Prusty. Takes as input a Rust program with some additional specification, and as output translates this Rust program to the so-called Viper language. Viper is an intermediate language for verification. And if there is any verification error in this program, then the tool translates the error spec to the original source code, pointing to the precise snippet that is wrong. If there is no verification error, then the function is ensured to specify, to fulfill the contract. Viper internally uses a SMT solver to check the proof. Let's give a better look at the translation that Prusty does from Rust to this Viper language. So, for example, consider the struct, the list. This is the definition that we saw in Rust. How is this translated to Viper? So, in Rust, when you have ownership on the list, meaning when you can modify the list, you can also modify recursively all the fields that are reachable, all the fields that are defined in this list. So we reflect this in Viper by defining a predicate list, which contains two fields, a value and the next pointer. And recursively, this list contains other predicates that define what is the first field, the I32 field, and what is the second field, the option box list. So since ownership is transitive, in our encoding to Viper, we have nested predicates to encode structures that are defined in Viper. So how is this predicate list used? We saw before that when we have such a client function with two mutable reference parameters to lists, then we want to specify that this function as input takes two lists that are disjoint, so they don't share any node in memory. And this can be translated quite easily in Viper using specifying that this function client requires as input to have these two predicates that represent these joint memory locations, but also this client function ensures to the caller of this client function that the two lists are still valid lists and are still disjoint once the client function terminates. Now, there is a more challenging case in Rust the case of the so-called reborrowing. So reborrowing is a particular pattern in Rust. When you have a function that takes as parameter a mutable reference to a data structure, for example, a binary tree, when the function returns a subtree of the data structure, this is called reborrowing. So from the point of view of the caller of this getter function, what is returned is still mutable because the return type is a mutable reference to a binary tree. But what is left of the initial tree is frozen from the point of view of the caller. Frozen means that you cannot read nor modify those parts that are no longer reachable of the tree. But once the returned reference goes out of scope for the caller, then the whole tree becomes mutable again. And you can see that whatever you modified using the returned reference is visible in the original tree. Now, there are two challenges in the encoding of this. For example, what is the ownership that is represented by this tree with a hole in it? You don't know exactly what is the path that leads to the subtree that is returned. So this is not trivial how to encode. And as a second challenge, what is the combined effect that the modifications that you did on the returned subtree, what is the effect that the modifications done on the subtree has on the original tree? So you have somehow to rename the effects, and this is not trivial. So in our work, we solved the first problem using a so-called magic wand construct from separation logic to specify what is the permission of a data structure with a hole in it. So I will not go in more details, but you can give a look at our paper or ask us offline. And for the second challenge, we developed a novel specification feature called pledge to specify how the changes done on the subtree can be reflected on the original tree. So for more details, give a look at the paper, ask us. There is not enough time to go much into details. So our work, we evaluated our work using in two different ways. In the first evaluation, we took the 500 most unloaded packages from the official Rust package manager, crates.io, and without adding any additional annotation, so without adding a contract, we filtered those functions that are supported by our tool, so roughly 20%, and we ended up having something like 40,000 lines of code. We then ran Prousty on these functions, and in those cases of the functions that we encoded, the core proof that we produce actually verifies fine how as expected. And in total, our tool produces 1 million lines of Viper code from the original 40,000. And 10% of the produced lines of the proof are auxiliary annotations. And you can see that there are roughly 2 and something lines of annotations for each original line of Rust code. In the second evaluation, we took some examples from the Rosetta Code website, some binary search and other algorithms. And in this case, we added a functional specification. So we added a contract to specify what the function does. And we checked them with our tool. We measured, we report in this table how many lines of code and how many functions are in each program. We report how many lines of specification we added to each example. And we measured how long does it take for Viper to verify this example. So these are the properties that we verified, but let's give a look at one particular example, the binary search. You can see that what happened? With just 2 lines of code, you can verify that the function does not panic and does not overflow. But if you want to pay something more, if you want to add 27 lines of specification, then you can also prove that the function actually returns the correct result. So you can opt in with the functional specification that you are interested in. So this is a very quick summary of our work, what else is in the paper. So we define what is the Viper encoding from Rust to Viper. We describe the automation, how we automatically generate the auxiliary, how we automatically generate the annotation needed for the proof. We describe how the pledges is implemented and what is this pledge feature. And we define the subset that is supported by our tool. So in conclusion, in our work, we dramatically simplify Rust verification using the information coming from the TAP system. And we believe that this approach will enable verification by developers. So this is the link to our work. You can use our tool is available on GitHub, and so also the ID extension that I showed in the demo. And thank you for your attention.
Thank you. Any questions? I'm sure there's many. Yes?
Thank you very much for the talk. You mentioned in your evaluation that you parsed crates to extract functions and you had no specification. So what is it that you verified in those functions?
So we verify the core proof, meaning that so when you verify a program, as I showed in the first slides, you have to mix the ingredients to specify, for example, how the memory is structured, what can actually alias what. And in our proof, in our work, in our core proof, we check that what is automatically generated is actually correct, meaning that, for example, if the Rust compiler actually allows a program in which, I don't know, at the end of a function, A and B, the first example that we saw, are no longer share some memory location, then that will be an error. So we use the core proof. We check the core proof in order to check that our encode is correct.
So if I understand correctly, basically you prove the claim Rust does on the signature of the function.
So if you, yes, in practice, yes. We've shared the references. We do something slightly different. We explain in the paper what we do. But if you exclude shared references, then yes, we check the type system.
Thank you very much.
Welcome.
Questions? Okay, so my question is, what are the limits, as in what can, apart from, what you presented on the slides, what other stuff can, prove with this framework? As for instance, let's say you have two mutexes. Can you show that if I acquire them and releasing them in that specific order, there is no way I'm going to deadlock? Is it possible to prove that sort of thing, for instance?
So, at the moment, a mutex would require some unsafe code. Mm-hmm. Well, a mutex is implemented with unsafe code. So at the moment, what we allow is to specify a contract that is trusted by the implementation of the mutex and is checked only from the point of view of who calls the mutex. So we don't, we have no example in which we actually use a mutex. So I cannot say that we support it, but what you can do in the presence of unsafe code is you can specify a function that describes the abstraction around the unsafe code. So you can use that function, that contract, to check that some functions are called in the right state, mm-hmm. But we don't check that the function is actually implemented in the correct way.
Okay, thank you.
In the demo, I noticed that Prusti said, I didn't find any quick fixes. I was curious as to what it could find conceivably and what could suggest to you.
What do you mean with quick fix? Maybe it's just the IDE that shows there is no quick fix available. We use a generic framework for our tool.
Okay, so Prusti is not attempting to offer...
No, does not try to fix the problem.
Okay, thank you.
Yeah, last question.
I found the second evaluation part where you are showing several examples where you give the functional specification and you can prove the functional specification without giving any help to the tool. Very interesting. I was wondering what would happen if you took these examples, wrote them in a different programming language, and encoded in the just added to the preconditions the separation properties that are given to you from the Rust type system. In that case, would the proofs also go automatically without any help from the user? This is my first question, and I want to ask another one. I think that ultimately you will hit a point where you will need to also get some help from the user to get the proofs to go through. So what would it look like? How will the user use the extra leverage that you offer from the Rust type system and everything that you can deduce from it?
Yes, thank you for the question. So I will just take the Rust example. So the first question is, what if someone also specifies that A and B don't share any memory location between them? Can also the proof go through automatically as in our tool?
And use a different tool, not your tool. Some other tool, all you do is
and use a different tool. Yeah. So in Viper, you can specify what is you can provide the functional specification of a tool, of a function, and also specify how the two elements are, the two parameters are disjoint in memory. And that's actually something that it's possible to do, but we don't ask the developer to add this part, because then they need to understand what is a separating conjunction and other small details of the underlying separation logic. And so I believe that if other tools support the same syntax that we do and use a similar program logic, then they can also encode the proof to an SMT solver or use, I don't know, Coq or something else if the one that verifies the program wants to manually build a proof. So I believe yes, one can reuse. Technically, we don't provide an interface, but it's a technical challenge only. Regarding the second question, so what if the tool does not go through automatically? So that's a common problem if you only rely on an SMT solver to discard your proof. And it is possible to provide some hints to the developer, to the proof solver. And we don't support them at the moment, but it is possible to, for example, split the proof in two. For example, if you have a big function that does a lot of things, you can split that big function in two smaller functions. So from the point of view of a software developer, that's also something that can be beneficial. And so to be short, it is possible to split the verification in multiple steps, but we don't support it in our tool. Does this answer? Okay, we can talk.
So this is really cool. And one thing that struck me is that when you find a verification error, the examples that you've shown on screen just say the precondition may not hold in all circumstances. My guess is that what's happening under the hood is that you're getting an unsat from the underlying SMT solver. And I'm wondering if there's a path forward to using the unsat core from that to map back to the surface programming language and explain to the user what is an unsatisfying a counterexample to show what the problem is.
So two things. First, our tool actually translates the proof to negates what you want to verify. So if you want for your program to be checked, then you want to get an unsat result for the proof. So if you get a sat result, it means that the checker found a counterexample. So In theory, it is possible, and we have other colleagues that are working on this, but this is not used. This is not supported by the implementation of our tool. So in theory, yes, it will be possible.
It would be really sweet.
Thank you.
Well, thank you very much. Thank you very much. You've received certainly a lot of questions, and I wish you a lot of luck with the queuing and lunch.
Thank you.